Welcome friends. So in the last part we have discussed first superposition theorem and then Thevenin's theorem, and we have solved one problem each from each theorem. Now today this part we shall discuss maximum power transfer theorem. So from the Thevenin's theorem what we have understood that if we have a voltage source ETH and if we have a RTH and if we have a RL, then we find out the current flowing through the load resistance I by a simple relation. It is ETH over RTH plus RL. Now for the time being, now this maximum power transfer theorem is an application or extension of Thevenin's theorem. What it actually states that, let us say consider for this load resistance we have a variable load resistance. So its value can be altered. That means let us say it can be varied from 1 ohm to 100 ohm. So naturally if we can vary the value of RL, then current will also vary. Current will be also vary. So as a result the power loss in the RL will be also vary. So as RL varies, therefore we can say that current will be varying, right? As a result, power loss is also varies. So now that is our main intention, that under what condition we can expect maximum power. Under what condition, that means under what condition we can expect the maximum power to be transferred from the source to load. That means our intention, that is why this theorem is called maximum power transfer theorem. We should search or obtain some condition at which maximum power can be transferred from source to the load. That is our objective. So that is exactly the statement of the maximum theorem, is that, again it's a general statement for a linear active bilateral network. Maximum power can be transferred if there are three conditions. So if you vary RL for a DC network, the first one is for DC network. If you vary your RL, then maximum power will be transferred when your RTH becomes RL. When this condition prevails, then at that condition maximum power will be transferred, and the nature of the power transfer is this. So in x-axis we have RTH, in x-axis we have RL. It varies from some minimum value to a maximum value. In y-axis you have PL, that is load power. So it follows a curve like this. So when it meets this condition, that means at this condition Thevenin resistance equal to load resistance. At this condition we have maximum amount of power. What is the proof? So from the Thevenin's theorem, you have the current relation ETH by RTH plus RL. So power transfer is nothing but I square RL. So ETH square plus RTH plus RL whole square into RL. So that to maximum power to be delivered to RL when we have dPL equal to 0. So if you take the derivative and if you solve, you will get this result. So when RTH is equal to RL, RTH or R Thevenin is equal to RL, so at that point of time you will get maximum power transferred to the load from the source. That is the case number 1. It is strictly for DC network. Now when we have AC supply, then what should be the condition? So we have case 2. So we have a source, again ETH. We have a RL. This is variable resistance. Now Thevenin equivalent impedance is RTH plus JXTH. Now it is not a resistance anymore. It is a Thevenin equivalent impedance which has got a resistance part and as a reactance part. Okay, that is the new thing added. So what will be the condition? The condition is, go back to the theorem statement. So when case 2, it states when Z Thevenin becomes RL, for an AC network with ZL is equal to RL. That means we have only load impedance is equal to RL. That is the load impedance only. We have, this is the only load impedance. Load impedance has only resistance. Okay, so with that, when we have ZTH is equal to RL, so at that condition we can expect maximum power to be transferred from the source to load. That means what is ZTH? ZTH is nothing but root under RTH square plus XTH square. So this is the ZTH for you. So when RL becomes this value, RTH whole square plus XTH whole square, then under this condition maximum power will flow from AC source to the resistive load. Now what is the proof? So using the same logic, we have first I is equal to ETH by ZTH plus RL. Now initially, so far it was RTH, but in this AC circuit we have ZTH. So we have substitute ZTH is equal to RTH plus JXTH. We have substitute RTH plus JXTH. So RTH and RL taken altogether in a bracket and J term is kept separated. So its magnitude becomes this. So power to be transferred again I square RL. So ETH square and divided by this RTH plus RL whole square plus XTH. Now to have the maximum power delivered to RL, you must have dPL by dRL is equal to 0. So if you solve this equation 10 and if you take the derivative of equation 10 with respect to dRL and if you solve, you will get this result. ZTH whole square is equal to RL square. So therefore ZTH is equal to RL. That is the proof. So in case of a resistive load, when you have Z Thevenin is equal to RTH plus XTH, so that load resistance must be equal to Thevenin equivalent impedance. That is the magnitude of the Thevenin equivalent impedance. That is the proof for you. Now moving forward with our last case, that is now again the third case is again for AC network. Now in this case we have the case number 3 is that we have a AC source. Okay, we have a Thevenin equivalent impedance, that is that already done. Okay, but in this case what is newly added thing now, in this case we have load impedance is equal to not only resistance but it has a reactance part, right? This is a variable impedance now, not a variable resistance anymore. It is a variable impedance now. So source is ETH, which is AC source. Now Thevenin equivalent impedance is RTH plus JXTH. And now in this case, what is ZL? We have RL plus JXL. Now with this, we have now going back to the statement. Now under this condition, when this Z Thevenin becomes ZL conjugate, when Z Thevenin becomes ZL conjugate, for that condition, under that condition, we have maximum power to be transferred from the source to the load. What does it mean? Let us give you an example. Let us say ZTH is equal to 2 plus J3. When ZL becomes ZTH conjugate, that means 2 minus J3. Conjugate means this 2 minus J3. So when this happens, then maximum power will be transferred from source to load. So the condition is ZTH is equal to ZL conjugate, right? So what is the proof? So again we have I, that is ETH by ZTH plus ZL. So if you substitute ZTL and separate resistive and reactive part, we will have this, and we will have the magnitude as this. So power transferred is I square into RL. So we have this equation. Now you need to take derivative twice. First you need to take derivative with respect to RL. You need to check under which condition, that is the rate of change of power with respect to XL and RL. So we have already done the RL part previously in the previous case example. Now we need to evaluate the same thing for XL, DPL, DXL, and when you solve this, you will get XL becomes minus XT. So from there, you can directly substitute. If XL becomes minus XT, they cancels out each other, and the maximum power transfer becomes this. So ZL must be equal to ZTH conjugate, or reverse is also true. So if ZL or ZTH becomes 3 plus J4, then ZL must be equal to 3 minus J4 in order to transfer maximum amount of power. So as we can see that maximum power transfer theorem is the extension of Thevenin equivalent Thevenin's theorem. We use the Thevenin equivalent network to obtain the maximum power transfer condition. We have seen 3 different conditions for DC circuit and for AC circuit. So with DC circuit, if RTH becomes RL, then that condition maximum power will be transferred. We have seen for AC circuit with ZL equal to RL, that is only resistive load is there, then that RL must be equal to the magnitude of ZTH. And the case number 3 we have seen when ZTH is impedance and ZL is also impedance, then they must be complex conjugate to each other in order to obtain maximum power transfer from source to load. So with this I am ending this part here. From the next session we shall discuss our last topic for this module, which is called Norton's theorem. Again, another important theorem of this network solving techniques module. Okay, with this I am ending here. Thank you.